So today we are going to discuss the differences between binary tree and binary search tree. So what's a binary tree? Binary tree is a data structure in which each node has most two childs. One is referred to as the left child and another as the right child. So we have an example over here. So 5 is the root of the binary tree. 6 is referred to the left child. 8 is referred as the right child. What's a binary search tree? Binary search tree is a special kind of binary tree wherein the left child is always smaller than the root and right child is always greater than the root. So in this case 6 is greater than 5. So this is not a binary search tree. So what would be an example of a binary search tree? Let's take the number again. 6, 5, 8. So let's look at this case. 5 is smaller than 6. So this condition is satisfied. 8 is greater than 6. This is also satisfied. So this is an example of binary search tree. Here we have an example of a binary search tree. Let's verify a few things. This is our root. For this root, this is the left subtree and this is the right subtree. So all nodes in this subtree would be smaller than the root. So we have 30, 20, 40, 32, 34, 30. All of them smaller than 50. In the right subtree, we have 70, 60, 65, 80 and so on. Everything bigger than 50. So we can take any node and for the left subtree and the right subtree, the left subtree would not have any node which is greater than the root, and for the right subtree there would be no node which is lesser than the root. So now let's look at how to search in a binary search tree. Let's say we have to search for a number 32 in this list. Okay, let's look at how to search in a binary search tree. Let's say we have to search for the node 32 and we have a pointer to the root. So since we know that the left subtree would always be smaller than the root and right subtree would always be greater than the root. So we compare this node we have to search with the root. So 32 is less than 50. So we look in the left subtree. Okay. So we come to 30. This time 32 is greater than 30. So we go to the right subtree. Again we hit a number 40. 40 is greater than 32. So we look at the left subtree. So here we have found a number. Let's take another example. Let's say we have to find the number 75. So we start from the root and since 75 is greater than 50, we go to the right subtree. Again we hit a number 70. 75 is again greater than 70. So we go to the right subtree. Now we have the root as 80 and 75 is less than 80. So we go to the left subtree. And here we find our number. The search complexity for a binary search tree is order log n. Please note that this is only an average search complexity. The worst case complexity for a binary search tree is order n. So now let's look at the insertion problem. So let's say we have to insert a number 5 in this list. Okay, so we start from the root. Since 5 is less than 50, we go to the left subtree. Again 30. Since 5 is less than 30 again, we go to the left subtree. We have 20. Again the left subtree and we insert the number 5 to the left of 20. Let's take another example. Let's say we have to insert a number 77. Since 77 is greater than 50, we go to the right subtree 70. 77 is again greater than 70. We go again to the right subtree. Now we have a number 80. Since 77 is less than 80, we go to the left subtree. We find number 75. Since 77 is greater than 75 and it does not have a right child, so we put in 77 as the right child of 75. Now we have to see how do we delete a node from a binary search tree. So there are three possible cases. So case one is the leaf nodes. So all terminal nodes are leaf nodes. Deleting them is pretty easy. You just traverse to that node, you search for that node and remove it. Okay, so we can directly remove 20, 36, 65, 75 and 85. The next case is when we are removing a node which has a single child. So let's take example of number 32. So here what we can do is simply replace a child node with the parent. So 40 will point to 34 and we can simply remove this node. Okay, so this still maintains the binary search tree property where 34 is the left child of 40 and 36 is the right child of 34. Let's take another example where we are deleting node 34. So this also has one child. Okay, so we can simply make 36 as the right child of 32 and remove 34. This still maintains the binary search tree property because 36 is greater than 32. Let's look at the problem where a node can have two childs. So taking example of the node 70, it has 60 in its left and 80 on its right. So if we want to delete 70, we have to find the closest biggest number in the right subtree. Okay, so how do we do that? We go to the right part, right subtree, and then go to the farthest left node. So we go to 80 and then the farthest left node is 75. So 75 is the node with which we will replace 70. So 75 will be removed and 70 will be replaced. It will be replaced with 75. It was easy to remove 75 because there was no subchild of 75. So let's take the situation again where we want to, let's say, remove the number 50. So what's the number closest to 50? So it would be, we go to the right subtree and go to the leftmost node of the right subtree. So it would be 60. We'll replace 60 with 50, but we cannot replace it directly because it has a subchild. So what we'll do is we'll recursively replace this node with this node. So 70 would have a left child of 65. This pointer will go away. We'll remove 60 and this will be replaced with 60. So this still follows the binary search tree property where 60 is the root, 70 is the right subchild, 65 is the left child of 70. So 65 is less than 70 and 80 is greater than 70. So this still holds the binary search tree property. Now we'll have a look at the worst case scenarios for a binary search tree. For a binary search tree, a worst case would look something like this, which is like a completely unbalanced binary search tree. So in this case, deleting a node would be order n. This is for the worst case, and that would be while we are deleting the node 4. Similarly, inserting is also worst case is log n. When we have to insert a number greater than 4, let's say we have to insert a number 10, it will come to the right of number 4. So this is the worst case for binary search tree.